The partial information model. In this section, we show for external regret a simple reduction from the partial information to the full information model. The main difference between the two models is that in the full information model, the online procedure has access to the loss of every action. In the partial information model, the online procedure receives as feedback only the loss of a single action, the action it performed. This very naturally leads to an exploration versus exploitation trade-off in the partial information model, and essentially any online procedure will have to somehow explore the various actions and estimate their loss. The high-level idea of the reduction is as follows. Assume that the number of time steps t is given as a parameter. We will partition the t time steps into k blocks. The block, except it will also randomly sample each action once, the exploration part. The partial information procedure MAB will pass to the full information procedure FIB the vector of losses received from its exploration steps. The full information procedure FIB will then return a new distribution over actions. The main part of the proof will be to relate the loss of the full information procedure FIB on the loss sequence it observes to the loss of the partial information procedure MAB on the real loss sequence. We start by considering a full information procedure FIB that partitions the t time steps into k blocks, b to the 1, b to the 2, and b to the k, where b to the I equals to the set of I minus 1 times t over k plus 1, and so on until the set of until the element I times t over k. And uses the same distribution in all the time steps of a block. For simplicity, we assume that k divides t. Consider an RK external regret minimization procedure FIB over that k time steps, which at the end of block I updates the distribution procedure. Updates the distribution using the average loss factor, i.e. c to the tau equals to the summations of L to the t over the size of b to the tau, summing for all those t in b to the tau. Let ci to the k equals to the summations of ci to the tau, summing for all those tau starting from 1 to the k for the blocks, and c mean to the k equals to the minima of ci to the k, where the minima is taken among all i's. Since FIB has external regret at most RK, this implies that the loss of FIB over the loss sequence c to the tau is at most c mean to the k plus RK. Since in every block b to the tau the procedure FIB uses a single distribution p to the tau, its loss on the entire loss sequence is LFIB to the t equals to the doubling summation, summing with the tau starting from 1 to capital K, and with the inner summation summing for all those t in b to the tau of the term p to the tau times L to the t, which is equals to t over k times the summations of p to the tau times c to the tau, summing for tau starting from 1 to capital K, which is less than equals to t over k times the term c mean to the k plus RK. At this point, it is worth noting that if RK is equal to big O of square root of k log n, the overall regret is big O of t over square root of k times another square root of log n in the denominator, which is minimized at k equals to t. Namely, by having each block be a single time step. However, we will have an additional loss associated with each block due to the sampling, which will cause the optimization to require that k should be always far less smaller than t. The next step is developing the partial information procedure MAB is to use loss vectors that are not the true average but whose expectation is the same. More formally, the feedback to the full information procedure FIB will be a random variable vector C hat to the tau, such that for any action I, we have the expectations of a C I hat to the tau equals to C I to the tau. Similarly, let capital C I hat to the k equals to the summations of a C I hat to the tau summing for all those tau starting from 1 to k and capital C mean hat to the k equals to the minima of a capital C I hat to the k, where the minima is taken from among all I. Intuitively, we will generate the vector C hat to the tau using sampling within a block. This implies that for any block B to the tau and any distribution P to the tau, we have 1 over the size of B to the tau summing times the summations of P to the tau times L to the t, summing for all those t in B to the tau is equals to P to the tau times C to the tau, which is equals to the summations of Pi to the tau times Ci to the tau, summing with the index I starting from 1 to capital N, which is equals to the summations of Pi to the tau times the expectations of a Ci hat to the tau, summing for all those I starting from 1 to capital N. That is, the loss of P to the tau in B to the tau is equal to its expected loss with respect to C hat to the tau. The full information procedure FIB observes the losses C hat to the tau for tau starting from for tau in the set among 1 to 3 until k. However, since C hat to the tau are random variables, the distribution P to the tau is also a random variable that depends on the previous losses, i.e. C hat to the 1, C hat to the 2, and so on until C hat to the tau minus 1. Still, with respect to any sequence of losses C hat to the tau, we have that CFIB hat to the k equals to the summations of P to the tau times C hat to the tau, summing for all those tau starting from 1 to capital K, which is less than or equals to C mean hat to the k plus RK. Since the expectation of Ci hat to the k equals to Ci to the k, this implies that the expectations of a CFIB hat to the k is less than or equals to the expectations of a C mean hat to the k plus RK, which is less than or equals to C mean to the k plus RK, where we used the fact that the expectations of the minima of a Ci hat to the k minima is chosen between all I is less than or equals to the minima of the expectations of a Ci hat to the k, where the minima is chosen between all I. We just take out the minima from within the expectation to out of the expectation. So, and the expectation is over the choice of C hat to the tau. Note that for any sequence of losses, C hat to the 1, C hat to the 2, and until C hat to the k, both FIB and MAB will use the same sequence of distributions P to the 1, P to the 2, until P to the k, from 4.2 we have that in any block B to the tau, the expected loss of FIB and the loss of MAB are the same, assuming they both use the same distribution P to the tau. This implies that the expectation of CMAB to the K equals to the expectations of CFIB hat to the K. We now need to show how to derive random variable C hat to the tau with the desired property. This will be done by choosing randomly for each action I and block B to the tau and exploration time Ti in B to the tau. These do not need to be independent over the different actions, so can easily be done without collisions. At time Ti, the procedure MAB will play action I, i.e. the probability vector, with all probability mass on I. This implies that the feedback that it receives will be Li to the Ti, and we will then set Ci hat to the tau to be Li to the Ti. This guarantees that the expectations of Ci hat to the tau equals to Ci to the tau. So far, we have ignored the loss in the exploration steps, since the maximum loss is 1. And there are n exploration steps in each of the K blocks. The total loss in all the exploration steps is at most nk. Therefore, we have the expectations of LMAB to the T is less than or equals to n times k plus T over K times the expectations of a CMAB to the K, which is less than or equals to n times K plus T over K times C mean to the K plus RK, which is equals to L mean to the T plus NK plus T over K times RK. The theorem 4.6. There are external regret procedures that have regret RK equals to big O of square root of K times log n by setting K equals to T over n to the 2/3 for T which is greater than or equals to n. We have the following theorem. Theorem 4.17. Given n big O of square root of K times log n external regret procedure FIB for K time steps, there is a partial information procedure MAB that guarantees LMAB to the T is less than or equals to L mean to the T plus big O of T to the 2/3 times n to the 1/3 times log n, where T is greater or equals to n.